Beneath the Swiss Alps sits one of the largest batteries on Earth. Not built from lithium, not built from steel tanks, built from a mountain. Engineers hollowed out more than 20 kilometers of tunnels through solid granite, hiding an entire power plant inside the rock. No visible turbines, no giant powerhouse on the mountainside, just a mountain that looks almost untouched from a distance. But the strangest part isn't what they built inside it. It's why they believed a mountain could become one of Europe's largest batteries. This is the Limmern Pumped Storage Plant in the Canton of Glarus, Switzerland. On the surface, granite peaks, 2 alpine lakes, a handful of narrow roads. Underground, one of Europe's largest energy storage systems. Construction began in 2009, with the plant entering service between 2016 and 2017, after an investment of more than $2.3 billion. It can generate 1,000 megawatts and store 34 gigawatt-hours, enough to act as a rechargeable battery for an entire power grid. The story starts with a problem Switzerland couldn't solve above ground. As solar panels and wind farms spread across Europe, they began producing more clean electricity than the grid could always use. On a bright afternoon, supply would spike. By evening, it would collapse. The country didn't just need more power plants. It needed somewhere to store electricity. For decades, Switzerland built its grid around one resource: falling water. By the 2000s, roughly 3/4 of the country's electricity already came from hydropower. Wind and solar were growing fast, but they came with a catch. They only produced power when the weather cooperated, not when people actually needed it. In Glarus, engineers proposed something that sounded almost absurd: turn an entire mountain into a battery. Not a metaphor, a literal one, using 2 existing lakes and the 630-meter drop between them. High above the valley sat Lake Mutzi. Far below sat the Limmern Reservoir. If engineers could connect the two with tunnels and pump turbines, surplus electricity could push water uphill whenever there was too much power on the grid, then release it downhill within minutes whenever there wasn't enough. Regulators approved it. The utility company Axpo backed it. Construction began in 2009. On paper, it looked almost simple. 2 reservoirs already existed, so this was just plumbing and turbines connecting them. Nobody spent much time worrying about the fact that the site sat more than 2,000 meters above sea level, buried in some of the hardest granite in the Alps, reachable by almost no roads at all. Why would they? The lakes were already there. The elevation drop was already there. All that remained, on paper, was cutting a path straight through one of Europe's toughest mountains. That assumption didn't survive first contact with the mountain. Construction crews arrived to find a site that fought them at every step. The plant sat above 2,000 meters, where snow covered the ground for most of the year, and temperatures regularly dropped well below freezing. Oxygen was thinner. Steep granite cliffs turned routine tasks into climbing expeditions. There were almost no roads capable of carrying heavy machinery anywhere near the site. Suddenly, the hardest part of the project wasn't building the plant, it was reaching it. Engineers built an industrial cableway nearly 4 kilometers long, strong enough to carry drilling rigs, steel beams, and concrete across valleys that no road could cross. Where even the cableway couldn't reach, helicopters took over, flying hundreds of missions to move workers and equipment. In some sections, crews were lowered onto exposed rock faces on ropes, the same way professional climbers work a cliff. A temporary village was built partway up the mountain, so hundreds of engineers could live on site for months at a time, because commuting simply wasn't possible. Then came the rock itself. Beneath the snow was some of the hardest granite in the Alps. The rock was so hard, and the tunnel geometry so complex, that relying only on a conventional tunnel boring machine wasn't practical. So how do you hollow out an entire mountain without breaking the mountain itself? The answer engineers landed on wasn't a new machine. It was one of the oldest techniques in mining, refined with modern precision: drill and blast. Ironically, one of the project's biggest engineering breakthroughs wasn't inventing a new excavation method. It was refining one of mining's oldest techniques with millisecond electronic precision. Crews used hydraulic drilling rigs to bore a pattern of holes into the rock face, then pack them with explosives triggered by electronic detonation systems, timed down to the millisecond, so each blast broke rock in a controlled direction instead of scattering it randomly. Blast after blast, over years, more than 20 kilometers of tunnel opened through the mountain, some carrying water, others carrying cable, others connecting one chamber to the next. Every tunnel was then reinforced with concrete and secured with thousands of rock anchors. Because once you cut a hole through solid granite, the surrounding rock continually exerts enormous pressure on the excavated space. At the center of that tunnel network sat the real challenge: a turbine cavern roughly 120 meters long and up to 50 meters high, carved by removing nearly 315,000 tons of solid rock before a single piece of equipment could go in. Once hollowed out, the cavern was rebuilt from the inside. Steel reinforcement, more than 80,000 cubic meters of concrete, overhead cranes rated to lift 300 tons. None of it works without water. 2 steel penstocks, each almost 2 kilometers long and 4.5 meters wide, carry water under pressures reaching 70 bar, moving at up to 30 meters per second. At the bottom of those pipes sit 4 reversible pump turbines, each rated at 250 megawatts, together making up the plant's full 1,000 megawatt capacity. Together, they allowed the mountain to behave like a rechargeable battery, storing energy one moment, releasing it the next. Getting that power out required its own project, a new 17-kilometer, 380 kilovolt transmission line on 53 towers, many of them assembled by helicopter because no road could reach the ridge lines. After years of construction and $2.3 billion, the tunnels were finished, the turbines were installed, and the mountain worked exactly as designed. But the real question was never whether the plant could generate electricity. It was whether one mountain could change how an entire continent handles renewable power. For the hundreds of workers who spent years living in a temporary village high in the Alps, the payoff isn't something they'll ever see from outside. It's buried under granite, invisible from every road in the valley. For households across Europe, the payoff shows up as something they'll never notice at all. The lights staying on the moment a cloud passes over a solar farm in Germany, or the wind stops over the North Sea. That's the quiet function of a plant like Limmern. It doesn't generate new energy. At roughly 75 to 80% efficiency, it actually loses some in the process. What it does is move existing clean energy from the moment it's produced to the moment it's needed. Projects like this can't be built just anywhere. They require the right geology, steep elevation differences, and abundant water. And that combination is about to matter more, not less. As solar and wind capacity grows across Europe, the swings between surplus and shortage grow larger. Switzerland's retreating glaciers may eventually expose new high-altitude basins suitable for future reservoirs. But the same melting ice is disrupting the rainfall patterns the entire hydropower system depends on. Swiss engineers didn't solve a 21st century energy problem by inventing a better battery. They solved it with 2 lakes, a 630-meter drop, and a mountain that already existed. No new chemistry, no rare earth minerals, just gravity, granite, and a tunnel network most people will never see. Somewhere beneath the Alps, that mountain is quietly storing energy, waiting for the exact moment Europe needs it. So if the future of the power grid came down to one choice, would you trust it to a warehouse full of lithium batteries or to a mountain engineered to store energy for generations?